Hi everyone, welcome to Knowledge Quest 5. This is a longer Knowledge Quest because we will be looking at both fatigue review as well as shaft materials, layout, and stress. So some top level information about shafts. Generally, they are rotating members and they most often have circular cross-section. So the circular cross-section prevents warping, so that's why we use a circular cross-section over, say, a square or rectangular cross-section. Usually shafts are used in rotating applications, but you can have linear shafts, and the video will kind of talk about that. They're used to transmit power or motion and provide an axis of rotation or oscillation and control the motion of other elements such as pulleys, flywheels, gears, cranks, sprockets, or bearings. So pause here and using the text or other online resources, briefly read about what each of these mechanical components are to the extent that you feel like you'd be able to identify them on the quiz. Next, this short video, watch it, and the two questions that will come on the quiz are, why is case or surface hardening important for shafts? And then name a couple of methods of securing components such as gears and bearings to rotary shafts. So shaft materials is covered in chapter 7.2 in your textbook. So read through that, paying attention to the following two questions. What controls shaft rigidity, the material, geometry, or both? And then 2, when starting a shaft design, what material is appropriate for the first iteration? Then this next video will talk about shaft surface selection. It's also short. To pay attention to are what are key considerations when selecting shaft material or surface treatment, and then what type of material is best at resisting corrosive environments. Chapter 7.3 is a really good chapter. It gives some design guidelines for shaft layout. So I won't read these all to you, but you're going to read that chapter and then answer the following 7 questions. And then next, this is a figure I just pulled from the text. I like it because there's a lot going on, but it's an example of a stepped shaft supporting a gear, in this case, a helical gear. And essentially, can you determine the function of the shoulders in the shaft, and can you locate the bearings? So the functions of the shoulders, for example, are to position the bearings where they need to go. Also to position the gear itself. So the shoulders help position everything on the shaft. And then in this case, there are 2 bearings. So bearing 1 and again, bearing 2. Those are both tapered roller bearings because their rolling elements are at an angle. We are not going to be analyzing tapered roller bearings in this class, but they are often used in conjunction with helical gears because helical gears produce what is known as a thrust load or an axial load. So components like helical or bevel gears and tapered roller bearings produce forces that act axially or through the shaft. So in these situations, you need to somehow transfer the axial or the thrust load through a bearing to the ground. So that's what is being depicted here. We have a radial load that acts radially through the gear. And then because of the helix angle, there's also a force that's produced through the shaft. So in general, it's best to only have one bearing carrying the axial load, especially for long shafts. Okay, so stress concentrations in shafts is going to be one of the things that we pay a lot of attention to. And the interesting thing about shaft design is that you don't often know the total geometry of your shaft at the outset of a design, so you have to estimate your stress concentrations. But usually components are of standard proportions, meaning, for example, that you have to have a certain amount of shoulder height to support a bearing. So these standard proportions are what we use to estimate stress concentration factors. But it's very important that once the geometry of your shaft has been set and you have a working final model or drawing, you have to go back and refine your actual stress concentration factors. You can't use these initial estimates, which are shown on this slide, table 7.1. So put this in your analysis tool for sure. So table 7.1 gives some first estimate stress concentration values. And you can see how the stress concentrations are actually not specified by the geometry itself, rather by the type of geometry. So a sharp shoulder fillet, a well-rounded shoulder fillet, 2 types of key seats, and a retaining ring groove. So just looking at the numbers, you can see, for example, that a retaining ring groove is a lot worse for stress concentrations in bending. So what we would have with the retaining ring groove, something like this. So that compared to a simple shoulder, this is going to have the higher stress concentration. So I guess intuitively it kind of just makes sense looking at that drawing, but it's interesting to note that, for example, retaining ring grooves do yield such high stress concentration, so you don't want to like have them all over your shaft. Yes, so okay, I said that needs to go in your analysis tool. So short info on shafts, because we're going to dive into fatigue, but a little summary here. Shafts are used in all rotating machinery. Steel is usually the choice of material to obtain high stiffness for low deflections. Shafts may be of soft, low carbon steel or medium to high carbon steel for higher strength, or if a really hard surface finish is needed for wear resistance. Machine shafts usually have stepped shoulders for axial location of attached elements such as bearings and gears. But note that these shoulders create stress concentrations that must be considered in the stress analysis. Keyways or things like interference fits also create stress concentrations. And then lastly, the loading on shafts is usually a combination of torsion and bending, either or both of which can be time varying. So when you see this term, time varying, that means that we have to do a fatigue analysis. That's where we're going to head next. So fatigue review, I want you to start out by watching this intro to fatigue video. It's about 12 minutes long. I made it about a week and a half ago. And I think it's interesting. I think it gives a little history lesson and watch a video. So there will be questions on the quiz that pertain to this video, so definitely watch it. Once you're finished with that, we'll come back, and the next thing to consider is this difference between components in the laboratory under fatigue loading versus components in real life under fatigue loading. And there will be very significant differences between the fatigue strength of a test specimen, so something that is polished and perfect. Look at that nice shine on this test specimen. It's been polished axially. That's going to look a lot different than a component in service. So things like loading, shape, size, temperature, and corrosion all have a big impact on the fatigue strength of a component. The primary equation that we use to deal with fatigue strength is called the Marin equation. So this is something that you should have covered in 328, but we're going to review it here. So starting out, this SE primed. So this is the endurance limit of a test specimen. And the video talks about what endurance limit is. But we have to modify that test value endurance limit to better approximate the endurance limit of that component in service. So it's derated by all of these things: surface condition, size, load, temperature, reliability, and miscellaneous effects. And so you need to figure out each of those components individually and multiply them by SE prime to get the modified endurance limit. So the first step in these problems is determining SE primed, and that's a simple calculation. That is just 1/2 SUT. And then you go through all the factors. So the first factor is the surface condition modification factor, Ka. And this factor depends on the quality of the finish of the actual part surface and on the tensile strength of the part material. So here it is. Here is the ultimate tensile strength. And then you have these two factors, A and B, that you get from table 6.2. So copy paste this table into your analysis tool or just program the values in directly. You have 4 different surface finishes here. The exponent B isn't going to change depending on your unit system, but the A factor will change depending on if you're in PPSI or MPA. And I made this chart just because I was kind of curious at how these different surface finishes affect Ka. So you'll see that the best case for our components in terms of surface condition is round. Then machine or cold drawn, then hot rolled, and then as forged would be the worst case. So that Ka being 0.45 would really drag down the endurance limit. Size factor Kb, this is probably the weirdest factor, so we'll do a little example. But for rotating beam specimens, like the specimens in the lab, they're usually pretty small, about 1/3 inch in diameter. For larger parts, a size factor is needed to account for the fact that larger parts fail at lower stresses due to a higher probability of flaws being present on the surface of that material. So this factor accounts for that. So if you have something that is rotating, so let's say you have a solid rotating shaft, the Kb factor isn't that tricky. You just have to make sure that you are looking at your units. So are you in inches? Are you in millimeters? And what range is your diameter? So if you have something that's 1 inch, you'd use this expression. If you had a shaft with a 3-inch diameter, you'd use this expression. But that's only for a shaft that is rotating. What do you do when you have a round bar in bending that is not rotating? So say you have a 2-inch diameter shaft that is non-rotating. What is its size factor? The first thing you have to do, and I'm not going to go into this too much because it is 328 stuff, but you have to figure out the equivalent diameter. So the equivalent diameter is basically, it's kind of like accounting for the material that is more on the outside of the shaft, but it is a simple calculation. So 3.7 times 2 inches. So that is 0.74. So what we do is use that equivalent diameter in the appropriate expression for Kb. So now we have D, we have to use the equivalent diameter here, and that's always the kind of confusing part for people. So now we do 0.879 times 0.74 to the negative 0.107. So that is 0.907 for Kb. Cool. How would this answer change if your shaft were rotating? In this case, we would use this expression because our D is 2 inches or above. Okay, so I won't do the math, but you see the process. Okay, so loading factor. Estimates of SE primed are typically obtained from completely reversed bending, and the video talked about what completely reversed bending is. But we have to account in real life for different types of loading. So that's what KC does. So if it's bending, we have 1. If it's just axial loading, we have 0.85. If you have a shaft that is only in torsion, you use 0.59. Here's a note. When torsion is combined with other loading, such as bending, set KC equal to 1, and then the von Mises analysis that we'll do is going to manage that by combining everything. So unless you have pure axial loading, you're just going to set Kc equal to 1 and then deal with everything through Binding-Squeeze. Okay, temperature factor. This was just like the funniest equation, and it took me so long to type it in PowerPoint. But for operating temperatures below room temperature, brittle fracture is a strong possibility and should be investigated first, because when ductile materials are cold, they behave more like brittle materials. So above room temperature, yielding should be investigated first, and yield strength drops off rapidly with increased temperature. So that is essentially what this KD is accounting for. We're just going to be looking at things in room temperature for ease of calculation, and we're just reviewing the concepts. But just know that if you had something other than room temperature, you would have to modify. And I don't think you should definitely memorize that. That was kind of a joke. This is just an interesting figure. It shows the effect of operating temperature on the ultimate strength of steel. It's just showing that the ST is the tensile strength, the operating temperature, so whatever is the actual temperature, versus room temperature. And you see that that ratio goes down as the temperature increases. Reliability factor, KE, basically there is just a lot of scatter and fatigue testing data. You don't have to use this equation. So if you're given a certain amount of reliability, for example, 50% reliability, your reliability factor KE would be 1. And this reliability doesn't mean that you have a 50-50 shot of your part failing in fatigue loading. This is the reliability that the standard deviation of the reported endurance strength doesn't exceed 8% of its mean value. So I think what this basically means is that the higher reliability that you set is essentially saying that you are, more sure that the reported endurance limit that you're using, the endurance limit that you're using is closer to test values. But it's something that has to be given to you in the problem statement. All right, and then lastly, miscellaneous effects factor, KF. This is really meant to be kind of a reminder or a wild card where you can account for any other conditions you believe will decrease the endurance limit. So corrosion or electrolytic plating or metal sprain. Some of these things are used because it does increase corrosion resistance, but it can reduce the fatigue strength or frettage. So anything that's putting like little bumps or grooves, because fatigue failure happens at cracks. So when we have a bumpy surface, cracks are more likely to happen. And then about stress concentrations in more detail. So holes, grooves, and notches increase the stress in the immediate vicinity of the discontinuity. So in 328, we defined static stress concentration factors, KT and KTS. So the little s was when you had loading and shear. KT was for bending or axial loading. This little 0, this is nominal. That's what that means. And then, for example, your maximum shear stress is the product of the stress concentration factor times the nominal stress, which for us in that class is usually TC over J. Okay, so with ductile versus brittle materials, there's a difference in how they behave. So ductile materials have localized yielding or the presence of a discontinuity. So the material they had a hole, and this were ductile. So the stress will concentrate around this hole, but you'll also get some localized yielding and strain hardening, which serves to strengthen the part at that hole, that discontinuity. So we don't usually apply the stress concentration factor to ductile materials for this reason, but we do account for the reduced geometry. So sigma P over A That still holds true, obviously, for a ductile material. But if you were looking at the max stress, you'd use the area reduced. But you wouldn't necessarily have to tack on the additional AT to that. But in fatigue loading, you always have to use stress concentration factors, even when you do have a ductile material. We use reduced values of stress concentration factors. So KF and KFS. So this is torsion, anything that produces shear stress. This is for bending, for axial loading. And then stress concentration factors are reduced in fatigue loading, so they're not as high as the static stress concentration factors. And that's basically, I think of it because if something is oscillating between tension, and compression, there's some point in time where the fibers aren't in tension or compression, so you get a little stress relief. So that's the way that it makes sense, best sense to me, that we use these reduced factors for stress concentrations in fatigue. Okay, 2 more slides, I promise. Notch sensitivity Q. Materials have different sensitivities to stress concentrations, which is referred to as the notch sensitivity of a material. So in general, the more ductile a material is, the less notch sensitive it is. Brittle materials are more sensitive to notches because in a brittle material, a little notch is going to propagate a crack a lot faster, a lot greater than a ductile material. Notch sensitivity also depends on notch radius. And then notch sensitivity is experimentally determined. It ranges from 0 to 1. When you get a Q equals 0, your material has no notch sensitivity. And when Q equals 1, material has full notch sensitivity. This would be the conservative approach, but it's not what we usually use. We go through the process to figure out what our KF is through Q. So procedure, determine KT first, then Q, material dependent, then KF. Let's do a little example. Let's say we had, just pick something easy. Say we had a component that had an ultimate strength of 150 APSI and a notch radius of, easy to read, 0.06. Let me draw this over. I don't know, that looks about Q equals 0.88. So that's how to read that chart. Notch radius in inches is down below, notch radius in millimeters is up top, and then you have lines that are shared. Okay, so what will KQ05 quiz cover? Questions pertaining to shaft materials and layout that were presented earlier in this KQ. Being able to report stress concentration estimates without specified geometry, so that would be using table 7.1. Being able to report actual stress concentration estimates once geometry has been given to you. Conceptual questions about fatigue from this KQ, as well as that intro to fatigue video that was embedded within this KQ. And then lastly, using the Marin equations to calculate the endurance limit of a shaft given relevant parameters. That's it. I'm sorry my voice is really croaky. It's actually pretty late, but I spent a good portion of the day with my daughter at Lopez Lake, so I'm playing a little catch up before Monday morning. All right, see you soon. Bye.